There was a request to discuss a certain part of this 2026 January chemistry paper, Unit 4 paper. While discussing that one, I thought we can discuss both rate of the reaction part plus the doubt the student had. Okay, let's see what we are going to discuss today. So we are going to discuss section B, question number 13, part A, with reasoning one by one why we have to write those answers for these questions. Okay, let's see. First question says that, question number 13, part A says that nitrogen monoxide react with oxygen to form nitrogen dioxide. Okay, nitrogen monoxide react with oxygen gives you nitrogen dioxide. So they have done this reaction in different concentrations of nitrogen monoxide and oxygen, and they have found the rate of the reaction. What the question asks, they're asking to deduce the rate equation, justify your answer. So first we have to understand what is this rate equation. Actually, rate equation, or we call it rate law. So we learned that to rate of a reaction, rate means how fast a given reaction takes place. A rate of a reaction depends on the concentration of reactants. So simply, if the concentration of reactants are high, rate will also high. And if the concentration of reactants are low, rate is low. This relationship, how concentration of reactants affect the rate of the reaction, is given by this equation. So this is called rate law. It simply says that rate equals a constant time, we call this one rate constant, times concentration of the first reactant to power x. So this x, we call it order with respect to the concentration of A. So it simply says that if the concentration of A increased, what will happen to the rate? This power tells like how many times the rate will increase. We'll discuss some examples and see how this x affect the rate of the reaction. Times the concentration of the second reactant to the power y. Y is order with respect to the concentration of B. This is the basic concept of the rate law. Now let's see how we can use this rate law to identify when you increase the concentration of a given reactant, what will happen to the rate of the reaction. Right. These orders can have different values. Most mainly whole numbers. So they can be 0, the order can be 0, order can be 1, or order can be 2. Let's take this sample question. They say that consider following reaction and its rate equation. Now we have reaction A react with B plus C gives you D. And this AB, simple A, B, C, D letters are the molar ratios. Now they found that rate equals, the rate law says rate equals rate constant time concentration of the first reactant to power its order. So they have found the order which is 0. How we are going to find this order? That's what we are going to do this in question. Let's see how we are going to do it. Times concentration of the second reactant to the power 1. They have found that. What is the order with respect to B? Times concentration of the third reactant to the power 2. So this 0, 1 and 2, we call them orders. Now the question they are asking, what will happen if we double the concentration of A without changing the concentration of other reactors? Now I'm not going to touch B or C, only I'm going to increase the concentration of A. Let's see what will happen. So we know that the rate law they have given us. So rate equals rate constant time A to the power 0, B to the power 1 and C to the power 2. Now we have this one. This R is the initial rate. Now we know that in the new reaction we double the concentration of A. So 2 times A. So I should get a new rate. I hope I will get a new rate. So I call the new rate as R dash. Right. Then what I'm going, that's my new equation for the new rate. Now what we are going to do is, so let's write R dash, rate constant is still there. I will take this 2 out. So whatever inside this bracket will get this power also. So therefore I will get 2 to the power 0 out like this. So this is the equation. I want to take this 2 to the power 0 even further front. So it's new rate R dash equals 2 to the power 0 times rate constant time A to the power 0, B to the power 1 and C to the power 2. Can you see this and this equation are the same? So that means this part represents the initial rate. So we can say that new rate is equal 2 to the power 0 times initial rate. 2 to the power 0, anything to the power 0 is 1. So that means new rate is equal to initial rate. That means rate will remain unchanged. All this time we were thinking when we increase the concentration of reactants, the rate will increase. But we found a reactant, we double its concentration, but nothing happens to the rate. Why is like that? We haven't discussed that part also with the mechanism, because this question they check each and every fact. Now it's like this. Now when you take your class, let's take your batch party. So you have a batch party. There are some friends, when they are there, it's like 10 people are there. But there are some friends, they don't talk at all. So like this. But I love this movie. It's called Zootopia. In there we have this Flash. It's a sloth. In the sloths are like very slow and very quiet. So what will happen if you clone this sloth? Cloning means you make another copy of it, right? And you bring 2 sloths to your batch party. Nothing will happen. Nothing will change. You are just adding a new member, but the intensity of the party remains same. That's how our reactant A look like in this reaction. So in this reaction, it shows that even you increase the concentration of A, nothing happened to the rate of the reaction. But there are some friends or some people like this Judy. If you clone them, what will happen? Intensity of the party also doubles, or it might be 4 times, it might be 8 times, it might be 10 times, because they make it so noisy and everything. So therefore some reactants like that there. But here, this reactor, this A is like this Flash. Okay, let's go. What will happen if we double the concentration of B without change in the concentration of A and C? So that's the question asked. What will happen to the rate if we double the concentration of B without change in the concentration of other reactor? Okay. Now what I'm going to do is, I have the rate law. This is the initial rate. Now I'm going to double the concentration of B. Now concentration of B is 2 times. Now again what I'm going to do, I'm going to take this number in front. So 2 to the power 1 will come front, right? So I'm going to take it front here from all the way up to here. 2 to the power come front, then what is remaining? The initial rate. Rate constant time B to the power 0, sorry, A to the power 0, B to the power 1 and C to the power 2. That's the rate constant according to my first equation. Sorry, rate of the reaction. Then what will happen? So new rate, which is R dash, equals 2 to the power 1 means 2. 2 times initial rate. That means if I double the concentration of B, rate also doubles. That means there are some reactants, when you double their concentration, rate can be increased by 2 times. And there's another question they're asking. What will happen to rate if we double the concentration of C? Now I'm going to double the concentration of C for the same reaction. Okay, rate law we have. Now I'm going to double the concentration of C. Okay, I'm going to again take this number front. 2 to the power 2. So 2 to the power 2 comes front. Remaining is the initial rate. Okay, it says that new rate is 2 to the power 2 times initial rate. 2 to the power 2 is 4. That means when we double the concentration of C, rate increased by 4 times. Can you see? These orders 0, 1 and 2 tells us when you double or triple the concentration of a given reactant, how many times it will increase the rate of the reaction. So now we have to summarize it before going to our question. So we learned that if our order is 0, when concentration doubles, nothing happens to the rate. If our order is 1, when concentration doubles, rate will also doubles because 2 to the power 1. If our order is 2, when concentration doubles, rate will increase by 4 times because 2 to the power 2. Okay, now let's see how we are going to use it. Okay, now they're asking, deduce the rate equation, justify your answer. Okay, first we have to write the rate law. No? Okay, so we have to write the rate law. We have the equation here. So first we'll write the rate law. So rate law says that, okay, so we need rate law. So I write it rate law here. Rate law says rate equals rate constant time first reactant. First reactant is nitrogen monoxide. Here it's the first reactant. To the power x, I don't know what is the value of x. These molar ratios, they are not directly linked with these power orders, right? So if this is 2, it can't be 2 here. It can be 2, it can be something else. So therefore we call it x. And oxygen concentration to the power y. So now what they ask you to deduce the rate equation. Deduce the rate equation means I should find x and y. That's the idea here. Right. Now let's see how we are going to do it. Now when you look at this experiment, can you see if you take experiment 1 and 2, here concentration of nitrogen monoxide remains unchanged. They are not changed. But what you have to do is you have double the concentration of oxygen. 0.01 becomes 0.02. You double the concentration of oxygen. What happened to the rate? 0.00802 became 0.01604. If you divide these two numbers, you will see the rate also doubles. So therefore I can write that first point, when consider experiments 1 and 2, when concentration of oxygen doubles, rate also doubles. Therefore we can say that order with respect to oxygen equals 1, because we just learned that in the previous slide, if the order is 1, what will happen? When the concentration doubles, rate also doubles, right? So that's what how we found this value of y. Then we have to find another thing. You can see here experiment 2 and 3. I'll take experiment 2 and 3. Can you see concentration of oxygen is now fixed, right? Concentration of oxygen is fixed. What I have done here is I have increased the concentration of nitrogen monoxide by 4 times. Now, concentration of nitrogen monoxide increased by 4 times. Right. When the concentration of nitrogen increased by 4 times, how many times this one has increased? If you make the division 0. Let's do that one. 0.25664. I'm going to divide by 0.01604. If you divide by this one, it is 16 times. Okay, it has increased by 16 times. What is 16 in terms of 4? Because that will make me easier. 16 means we know that 4 squared. 16 means 4 squared. That means when you increase the rate by 4 times, this will increase by 4 to the power 2. That means what is the order? The power is 2. Because when you increase this by 4, this will increase by 4 to the power 2. Okay, let's write that one. So we can write, when consider experiments 2 and 3, when concentration of nitrogen monoxide increase by 4 times, rate also increase by 16 times. Rate increased by 16 times. Yeah, rate increased by 16 times. We can shoot it, bracket is 4 to the power 2. Therefore, we can say that x equals 2, right? So therefore, I can write the rate law now. Again, you can rewrite the rate law. Rate equals rate constant time order with respect to nitrogen monoxide is 2. Order with respect to oxygen is 1. If it is 1, we don't write it, so I just don't need to write 1. Okay, now let's see the marking scheme whether we have all the points. Experiment 2 compared to 1, the concentration of oxygen doubles while NO remains constant and the rate doubles. Oxygen doubles, rate doubles. First point done. Experiment 3 compared to experiment 2, multiplying the concentration NO by 4 times. Visasi increase the rate by 16 times. Done. The first order with respect to oxygen, we found that. Second order with respect to nitrogen monoxide, we found that, and we wrote the rate expression. Yes, we have all 4 marks, right? Okay, that's how we get the answer for these type of questions, right? Now let's go for next one. Calculate the rate constant for this reaction, include units in your answer. Okay, now what they are asking is, they are asking us to find the rate constant for this reaction. Okay, for that we need our rate law again. Okay, so we know the rate law. Rate equals rate constant time concentration of NO to the power 2 and concentration of O2. Right, now there's a one question some students ask. Now let's assume in the first question you made a mistake, right? You made a mistake and you got both these values as 1. Now let's assume you did both these values as 1. So 1 here, 1 there, right? Now some students ask, now previous one I lost the marks because I didn't get this one correct, right? Because this is supposed to be 2 but I got it 1. Now how many marks will I lose in this question? None. The reason is because you already did a mistake. For that mistake you were already penalized, mark in the previous question. They removed your mark from the previous question, so they won't do anything here. So they will check whether you have done the calculation here perfectly using this incorrect the rate law, and if you get the right answer you get full marks, because this is called error carrying forward. We call it ECF. So if you do a mistake and if you already penalized for that mistake, they will not reduce any more further marks for that mistake again. That's one point you have to remember, right? So in our case we don't have to worry about it. So we have the rate law, so which we have the correct one. So rate law equals rate constant time NO nitrogen monoxide to the power 2 and O2 to the power 1. Okay, now let's take any experiment. I'll take the first one. Okay, any experiment. Now let's see what we know here. Do we know the rate for the experiment number 1? Yes, 0.00802, and it's better write the units here, right? Because we need them. So rate unit is moles per cubic decimeter per second, because in the question they ask include units in your answer, so you have to have the units. Rate constant, that's what I have to find, times concentration of NO. Concentration of NO, do I know concentration? Yes, it's there. It's 0.001 to the power 2. Again we have to add the units, so just keep this space for units, to the power 2. So what is the unit we have is, it's a concentration is mole per cubic decimeter, right? Times concentration of O2, 0.001 moles per cubic decimeter to the power 1. Okay, so this is moles per cubic decimeter. So we need to find rate constant, so we'll make rate constant as the subject, right? So I want to isolate rate constant in one side. So I just keep the rate constant there, it is okay. So rate constant is here, right? So now we have to take all the things to other side. So let's see what we have here is 0.00802. We have moles per cubic decimeter per second. This whole thing divided by. So here we have 0.001 squared times 0.001 to the power 1. Then we write the units. Here we have moles per cubic decimeter square. So what I did was I just took all this thing to the other side. So when something goes on one side goes to other side, when the multiplication goes to other side, it will become a division. That's why they are in the denominator. So we have mole per cubic decimeter to the power 2. Mole per cubic decimeter to the power 2 means mole per cubic decimeter multiplied by another mole per cubic decimeter. And we have another mole per cubic decimeter remain here. So another mole per cubic decimeter remains here. Adjust this rate constant a little bit farther away. Okay. Now we have everything on one side. Now let's simplify it. This mole per cubic decimeter, this mole per cubic, we can cancel out. So we can do the simplification. When you do the simplification, we will get the answer as 8.02 into 10 to power 6. Okay, and let's see what are the other things. We get mole multiplied by mole. So what you get as unit is, here we have per second on the top, and the bottom we remain mole times mole, it will be mole squared. dm minus 3, dm minus 3, it will be dm minus 6. Now we have to take them up. So therefore our rate constant, final rate constant should be equals 8.02 into 10 to power 6. Mole squared comes up, it will be mole minus 2. dm minus 6 comes up, it will be dm plus 6, and per second s minus 1. That's how you get the answer. Can you see this s minus 1? Shall I dm 6 s minus 1. Okay. Now let's see the answer. What we have here is, okay, yes, we have dm6 mole minus 2 per second. Yes, value is there, 8.0 10 to power 6. Yes, you get 2 marks for this question. Right. Now there's another question. The reaction of nitrogen monoxide with oxygen is thought to be a two-step reaction mechanism. First step of a proposed mechanism is shown. They have given the mechanism, first step of the mechanism. Suggest an equation for the second rate determining step of the mechanism. Justify your answer using your rate equation from A1. Okay. Suggest an equation for the second rate determining step of the mechanism. Right. Now we have to understand how this mechanism and the rate law link with each other. Without knowing that one, it will be difficult for us to do this, answer this question. You can answer it, but it's better to know the basic concept behind these questions. First thing is, basically reactants which are participating in the reaction will appear on the rate law equation. If you look at any rate law equation, you can say that reactants are the ones which are appearing on the rate law. So can you see here? In the rate law, you can see reactant A, reactant B, reactant C. The reactants are the ones who took part in the rate law. So that part we can understand. Okay. So in the rate law, always reactants will appear there. The second point is the thing we are going to understand here. The second point says that the orders with respect to each reactant will represent the number of molecules which participate on the slowest step of the mechanism. It's a little bit a confusing statement. Let's see, try to understand it. This is orders with respect to each reactant will represent the number of molecules which participate on the slowest step of the mechanism. You take the slowest step of the mechanism and the orders are equal to the number of molecules taking part in the slowest step. To understand that one, we'll take a mechanism. We'll take an example and we'll try to understand it. To understand this concept, I'll take this equation. When you have a halogenoalkane means it's an organic molecule hydrocarbon where one of the hydrogen atom is replaced by halogen atom. So it becomes halogenoalkane. When they react with aqueous base, aqueous OH minus ions, what will happen here? OH minus ion comes and replace this halogen atom, forming an alcohol. And the halogen atom moves out as halide ion. So OH minus jumps in, replacing the halogen atom. It occupies the space and the halogen atom moves out. That's the basic concept here. This can be done in two ways. Now let's assume this is our halogen atom. We had the bromine atom now. Okay, this is our carbon, whatever the molecule, right? This is the carbon chain. Now this carbon chain has a halogen atom. Our OH minus has two options. First option is it can wait. It will wait until this halogen atom moves out as the Br minus ion. So when the halogen atom moves out, halogen atom is out, now the OH minus ion jumps in and occupy the position. That's the first option this OH minus ion has. Wait until the halogen atom moves out. We call that type of movement SN1 mechanism. Why it is SN1 mechanism also I'll call it. I'll tell you why it is called S and N. S means as a substitution because one was there. You have learned about in some sports they have something called substitute player. Substitute player is when one is missing, you replace him. So this is a substitution. OH minus ion comes and it replaces the halogen atom. So it's a substitution. Of what? A nucleophile. Who start this reaction? OH minus. Minus means one who has electrons, lone pair of electron, which can donate. So the negative charge or anything with lone pair of electron which can donate, we call them nucleophile. Now it's a nucleophile. Nucleophile is performing a substitution. That's why I call it SN1. Why it is 1, I'll tell you right in a while. The example for this SN1 mechanism is when you react tertiary halogenoalkane. What do you call tertiary? When a carbon atom is attached to a halogen atom, if that carbon atom attached to 3 R groups, it's not hydrogen atoms, they have some alkyl groups or 3 R groups like this. 3 CH3 group attached to this carbon atom. So it's a tertiary halogenoalkane. For that one, when you add OH minus ion, what will happen? It will take place in 2 steps. This reaction takes place in 2 steps. What happens in the first step? First step, this halogen atoms moves out taking the pair of electron from this bond, the covalent bond. It takes pair of electron, forming the halide and it moves out, leaving a positive charge on the carbon atom. We call it, this is intermediate carbocation. This step is very slow. Why it is slow? Because you are breaking a bond. A nice covalent molecule break a bond, form a cation. It's making it unstable. That's why it's very slow. It's a tough decision to make to destabilize your molecule. Then what will happen? As soon as this carbocation is formed, it's attracting electrons because it's positively charged. Then OH minus ion really fast will come and join with this positive charge, forming a new covalent bond. Then the second step is fast. So this happens in 2 steps. Then when we look at the rate law for this reaction, we can see that rate law is equal rate constant concentration of the 2 reactants. So this is one reactant, tertiary halogenoalkane, and this is the other reactant, OH minus. Yes, both reactants are there in the rate law. But they say that order with respect to tertiary halogenoalkane is 1. But the order with respect to OH minus ion is 0. Why is that? To explain this one, I'll take this journey. So since I am from Sri Lanka, I'll just use an example, but you can think, don't forget about the country. Let's see. Let's assume you are in an off-road journey in the middle of a jungle. You know that off-road journeys take a lot longer time, like lot of time, like sometimes they say this journey is like take 20 days or something like that. But let's assume you are in the middle of the jungle. To come out from the jungle, it takes 4 days. That's your first section, right? And your mother is at home and she calls you and she will ask, when will you be back in home? So when you will be back. So obviously you know that to come to this city it takes 4 days, but from there there's an expressway. So this express is so fast, within 1 hour you can reach your destination. Now when your mother asks when you will be back in home, you have two options. She's asking when you will be back. First option, you can say that I will be back in 4 days. Second option, you can say that I will be back in 4 days and 1 hour. Which one will you tell? What will be your answer? Yes, obviously your answer is A, because with respect to this small time, you don't talk about like I will take 4 days and 1 hour, because the 1 hour is insignificant. You don't care about it. So you will always focus on this 4 days because that's the slowest part. So if you want to speed up the reaction, you have to do something for this section A. You don't need to do anything for this section B because it's already fast. That's the same thing they are telling here. When you take this reaction, this is just like your off-road jungle journey. Alright, take 4 days. And this is just expressway. 1 hour. So if someone asks, how can I increase the speed of this reaction? You have to do something for this slower step. Alright, so obviously reactants are the ones will appear on the rate law. But we know that if I add, let's assume I am adding for this southern expressway, so what they call it expressway, instead of adding 4 lanes, I'm going to add another 4 lanes. So I'm going to make it 8 lanes. So I'm going to add 4 more lanes, right? So this is what I'm going to do. I'm going to add 4 more lanes. If you add 4 more lanes, what will happen? This 1 hour journey, you might be able to reduce for like by 40 up to 40 minutes. It doesn't make any difference. Doing anything for this step 2 doesn't make any difference on the rate of the reaction. If you want to speed your journey, you have to do something here. Something to make it faster. This 4-day journey. That's where you have to focus. So that's what we are saying here. So our idea here is, if we want to speed up this reaction, you have to do something on this slower step. That's why they say that if you want to increase the rate, do something for the reactant taking part in the slower step. That's why they have a power, which is 1. So if I increase the concentration of the reactant of the slower step, the rate of the slower step will increase. Rate of the slower step will increase means rate of the reaction will increase. But if you increase the concentration of the reactant in the faster step, it doesn't matter. You increase the concentration of OH minus like 100 times. Nothing happens because you are just increasing this faster step. If you make that 1 hour to 40 minutes or 30 minutes, it doesn't affect the time that takes to the whole journey. That's why they say that always, if you want to speed up the reaction, focus on the slower step. That's why when you reactant taking part the slower step has a more saying on the rate of the reaction, and they have a higher order with respect to the reactant. I hope you understood this one. If you didn't understand it, leave a comment. I'll explain it again. Okay, now let's go for second option. Now we were talking about there was halogen carbon atom is attached to bromine or any other halogen atom, bromine or chlorine. How this OH minus sign going to replace it, right? Alright, how this OH minus sign going to replace it? The second option, this OH minus has it can chase away this halogen atom forcefully. It can chase away this Br minus and forcefully and jump in. That mechanism is still a substitution because you replaced one of a nucleophile. Yes, is a nucleophile is the one who's doing it, and we call it SN2. Why it is called 1 or 2, I'll tell you in a while, right? Okay. Now let's go for mechanism of that one. That's called SN2 mechanism. This usually happens in primary halogen alkenes. Primary means you have the carbon atom where the halogen atom is attached, and that one has only one R group attached to it. Okay, that's called primary. One R group or no R groups. So when the OH minus comes there, what will happen? OH minus, look at this scenario, it comes and form a bond forcefully with this carbon atom. It loses lone pair of electrons and donate it towards the carbon atom, because carbon atom is slightly positive charge, because chlorine is electronegative, highly electronegative. So therefore, since chlorine pull the electrons towards itself, halogen atom, so this becomes slightly positive. So OH minus ion comes and donates its lone pair of electrons to form a bond. Okay, now the covalent bond is formed forcefully. So when the oxygen join, OH group join with this carbon cannot have more than 4 bonds, no? So obviously, chlorine atom, halogen atom will leave the molecule with pair of electrons, forming Cl minus ion. Now in this reaction, there's only one step. It's like this. You go to the exam, and you are the only child for the exam. And let's assume you get 80%. Someone asks, what is the highest mark of the exam? 80%. Someone asks, what is the lowest mark in the exam? 80%. Because you are the only one. Same thing. Now we have only one step. What is the fastest step? This one. What is the slowest step? It is the slowest step as well. So when you have only one step, what will happen? Again, reactant will appear on the rate law, but this is the slowest step, no? Anything you do to increase the rate of this reaction will increase rate of this step will increase the rate of the reaction. So therefore, order with respect to OH minus ion is 1. Order with respect to halogen alkene is also 1. Right, now why they are SN2? Can you see what is the total order? 1 plus 1 is 2. That's why we call it SN2 mechanism. Shall we go to the previous one? Why the previous one we call it SN1 mechanism? Can you see the total order? Here this is 1 and this is 0. 0 plus 1 is how much? 1. That is SN1. Substitution of nucleophile where total load of the reaction is 1. The second one we call it substitution of a nucleophile where total load of the reaction is 2. That's what we call SN2 mechanism. Okay, now you got the idea how the mechanism linked with the rate law, right? Now let's see whether we can understand what they are saying. Basically, the reactants which are participating in the reaction will appear on the rate law. That's fine. The orders with respect to each reactant will represent the number of molecules which participate in the slowest step of the mechanism. That's also right. Now, keeping that in our mind, let's go for this question. The reaction of nitrogen monoxide with oxygen is thought to be two-step reaction mechanism. Okay. The first step of proposed mechanism is shown. Okay, they have given the first step. This is the first step. So this is a reaction. We have it here. So reaction is, this is my reaction. So reaction is 2NO plus O2 gives you 2NO2, right? So we have this step 1. Step 1 is there given. Step 1 reaction is 2NO gives you N2O2. So that's you get N2O2. Two-step reaction. First step is the proposed mechanism shown. Suggest an equation for the second rate determining step of the mechanism. Okay, then we'll go for step 2. Right. Now they ask us to suggest a mechanism or reaction for this second step. That's what the question says. Okay, let's see how we can find this one, right? Now we can see that first we'll write the equation. Okay. We'll write the rate expression. Rate expression says that rate equals rate constant time NO to the power 2 and O2 to the power 1. That was our rate law, right? So we know this one. These are the molecules. So first thing is we can write that in the rate equation, so we can say that in the rate equation, right? So we can see that according to this equation, we can say that at this rate determining step, or we call it slower step, at the slower step, or we can say that rate determining step, so at this lower step or rate determining step, 1 mole of oxygen is needed because it is first order. Then you can say that, and 2 moles of nitrogen monoxide is required because it is second order. Can you see that? There's a different reason, but I'll tell you in the way that you can understand, right? Only to get more complicated. Can you see that this N2O2 is similar as 2NO, right? So N2O2 is there now, so we have to have that N2O2 in the second step. Whatever the product in the first step should have been in the second step now. And we know that N2O2 is same as 2NO molecules on the first step. There's a way we can link it in a mathematical way, but I'm not going to discuss that part. It will make you even more confused, right? I won't tell and make you to understand the concept easily. It's simply, right? So N2O2 is same as 2NO molecules. So therefore, this requirement I think is fulfilled in the second step. We call it rate determining step or the slower step, because they are saying that no. So I just an equation for second step, which is the rate determined. So this is our slower step, right? Okay. So what else we need? 2 NO molecules plus 1 oxygen molecule here. 1 molecule of oxygen. 1 mole of oxygen. Right. So therefore I have 1 oxygen. So when I do that one, I should get the products. So what is the product of the reaction? 2NO2. That's the answer for my rate determining step. Okay, let's see the marking scheme and see whether we have done it. Okay, the marking scheme says that these are the points in the marking scheme. Okay, so we have the slower step. Yes, 1 mark. 1 mole of water is needed to rate determining step. Yes, 1 mole of is there. 2 moles of NO is required for the rate determining step. Yes, we have that also. Therefore, our answer is complete. So we get full marks for this question. Right. Why I discuss all this part? Because I have this request. So this request says that, could you please MCQ explain this MCQ 3? Why is in the answer is not D? Okay. So why is not D? Now let's go this one. Why is not answer is D? Now we have the answer. This is a halogenoalkane reacting with aqueous alcohol. Okay, so aqueous OH minus. Now we have 2 mechanisms now, SN1 and SN2. So why this problem comes? Why this tertiary likes to go with SN1? Why this primary likes to go with SN2? There's a reason. The reason is, now let's assume I have the OH minus ion here. This OH minus ion wants to go and react with this carbon atom. Just like in SN2 mechanism, it wants to jump there and react with it. But it can't react with it. What is the reason it can't react with it? Because there's a problem. The problem is, when you have tertiary halogenoalkanes, these R groups are bulky. When the R groups are bulky, what will happen? There's no space for this OH minus ion to reach this carbon atom. Can you see that? So there's no space means it has to wait until this chlorine atom moves out, and it needs some space where this OH minus ion can reach this carbon atom. Now when you have positive charge, when there's nothing, there's a space for this OH minus ion to reach. That's why the tertiary like this SN1 mechanism. SN1 mechanism means in the slower step only one reactant taking part. That's why it's here. The other reactant cannot take part in the slower step. And if you go for this SN2 mechanism, now here OH minus ion has enough space. You can clearly see that. These are tiny hydrogen atoms, are very tiny atoms. So therefore enough ample step, only one CH2 group is there. So therefore ample of space, therefore OH minus ion can go there. Since OH minus can easily go there and attach to it, so therefore this SN2 mechanism is preferred by this primary halogenoalkanes. Okay, so now we have the idea, and why we know that why they call it SN2 and SN1. You look at the rate law. If the rate law shows only one reactant, can you see rate law only shows only one reactant taking part in the slower step. In other words, total load is 1. We call it SN1 mechanism. And in the rate, if the rate law shows there are 2 reactants taking part in the slower step, see 1 plus 1 is 2. That's why you call it SN2 mechanism. Now we'll get back to our question. The question is, why the answer is in D? Why the answer is not D? The reason is it is SN2. So can it be SN2? No, it can't be SN2 because can you see this is only one reactant is there. So it has to be SN1 mechanism. And you know what is this? Primary or secondary? If I draw this one, the halogen atom is attached to a carbon atom. That carbon atom is attached to 2 CH3 group. 2 CH3 group means it's a secondary. Class of halogenoalkane is secondary and it is SN1 mechanism. That's why our answer is C. So that's the one I wanted to answer. But then I realized that with that explanation for that answer, I can discuss this whole section A in the question number 30. Okay. So that's all from me. Thank you for joining with me. If you have any more doubts, just leave a comment below or like it. Then I'll get back to you with the answers. Okay. Thank you very much.